Hi everyone. In this demo, I'm going to show you how real-time fraud detection works using Apache Flink. What you're looking at right now is a real-time dashboard connected to a Flink streaming job. This dashboard updates live based on the events Flink processes. Right now, it's not showing anything because we've not started a Flink job. Flink is a distributed stream processing engine used when you need results instantly, not after minutes, hours, or batch cycles. Stream processing means it processes real-time streaming data, unlike static database data. It excels at handling unbounded data streams with exactly once guarantees, event time semantics, and very low latency. So today I'll walk you through the architecture, show the code, run real-time ingestion, and explain how Flink analyzes the data. To give you a quick real-world example, Alibaba uses Flink for real-time fraud detection on Valentine's Day, processing orders at loads of over 175,000 transactions per second. Netflix uses Flink for real-time monitoring and personalized recommendations, and Uber uses Flink to detect surge pricing conditions based on location streams. The reason they use Flink is simple. It processes data as it arrives and gives actionable results within milliseconds. So let's look at the code now. In this process, using three main files, the event producer, Flink fraud job, and dashboard. Now, event producer simulates live financial transactions. That's because I'm demonstrating Flink to detect financial fraud and we don't get access to actual financial data. Flink fraud job is the Flink streaming analytics pipeline, and dashboard is the Streamlit dashboard that you were looking at earlier, which shows you the results. Now let's walk through each one. The first one is the event producer.py. What it does is writes JSON events into the input events folder every 200 to 400 milliseconds. Each transaction contains a user ID, an amount, a timestamp, and an event time feed. This simulates card transactions coming into banks for fraud detection system. Now the next one, which is the main file, the Flink job, is the heart of the system. So first we create a Flink job using settings and t_environment. So you're creating a streaming environment which allows Flink to continuously process incoming files instead of a batch mode thing. Secondly, we need to define a source for the data. So how do you do that in Flink is you define a source table. We define it over the input events directory, because input events is what the event producer puts the events into. So here you can see the source table. This lets Flink ingest new events automatically. We also define event time, which is the timestamp of the event, and watermark, which is event time minus 5 seconds. Watermark is what helps Flink understand if an event is late or not. Now the next most important thing is the 10-second tumbling window. So this calculates total spending per user. If the user spends more than 8,000 rupees in that window, it emits an alert. So where's the tumbling window? Here. As you can see, this is the main tumbling window. This is a late out and a SEP like out table, which is used to handle late events. This is your main tumbling table actually. I apologize for that error. You can see that it defines a sum greater than 8,000, then it flags it as fraud. Next you have the late event detection table, which detects transactions that arrived later than the watermark. So this is late event detection, where say if a transaction takes longer than you expect, then it's fraud. And you have SEP like rapid spending. SEP is a form of credit card fraud. 3 or more high value transactions in a 5-second window, as you can see here, when count is greater than equal to 3 more than 3 seconds, that is also marked as suspicious, called a SEP alert. And lastly we have syncs. So you've got main insert, late insert, and SEP insert that puts files into JSON_out, late_out, and SEP_out. That allows Flink to take data related to window alerts, late events, or pattern-based anomalies. So these are the files that feed the data into the dashboard. And lastly, we'll look at the dashboard.py. What it does is it reads those folders, the output folders from Flink fraud job, and shows you window-based alerts, the amount every user spends every 10 seconds, a visualization of late events, SEP anomaly detection, that's very high, a high number of high value transactions in a short time, total spending over time and the most suspicious users based on the algorithm. So let's run everything. First we run the transaction generator, the event producer that simulates financials. So you can see we've got input events, and each event has a user ID, an amount, and a timestamp and transaction ID. Once we have the financial data being fed in real time, we can start the Flink job. That feeds into Flink output, and in a minute you'll see it actually processing the data from the input events file. So here you can see the JSON, SEP and late files. So it takes the data from the input events and it classifies as either a SEP alert or it's a late event alert, and so on and so forth. So you can see the transactions being written in real time and Flink processing windows, detecting patterns and writing into the folder. Now that Flink is written the first window, you can look at the Streamlit dashboard and you see we have actual data. So you can see the number of windows processed, that's 153 5-second windows, how many late transactions it's got, and how many SEP transactions it has seen. So SEP is basically how many users spend a lot of money in little time. So in this example here, fraud alerts, a window alert in red, means a user spent a lot of money in very little time. And you can see it has the name and what credit card tier they're using, as long as the alert type and how much they've spent. So then we have the top users. These are the people who've spent the most, obviously. And we've got the total amount per window. That means for each window is the total amount of spending increasing or decreasing. This helps to track whether a transaction aligns with the patterns we're used to seeing or if it's anomalous. SEP alerts means they triggered suspicious behavior for spending a lot of money in very little time. And late events show that Flink can handle out of order data. Now, watermark movement demonstrates Flink's event time model. So this event time versus processing time, late events, shows you how Flink handles late data, and a watermark is like saying the average time, and if it is later than the average time, then it's classified as a late transaction. So you can see the delay by how late. So index is the transaction ID and delay is how late the transaction is. This is mostly how real fraud detection systems in banks work. They combine rule-based windows, pattern detection, and late event handling. So that's the full pipeline: live data generation, real-time Flink streaming, event time windows, late event detection, SEP style pattern matching, and a real dashboard that shows all your results. As you can see, this demonstrates why Flink is used in production for fraud detection, monitoring, IoT analytics, and high volume real-time decision systems. Going back to the code, you can see that the Flink fraud job is still running. It's processing all the data that's being produced in real time by the event generators. So Flink is really proving its worth as a tool to process very high speed and very high volume data in real time. Thank you.